Hi, in this video, I'm going to go through the AQA AS-Chemistry paper 1 from 2019. And this is the second half of this paper. The first half of it I did in an earlier video. Okay, so question 6 is about titration. Solution: does an investigation determine the MR of an unknown diprotic acid, H2A, which reacts with sodium hydroxide like this? Diprotic, so it's a 1:2 ratio. Okay, so we'll read this in a minute. So let's do it now. 250 centimeters cubed of solution were prepared using this much of HA, so that's 1.3 grams. Okay, so I'm going to draw. So we've got a volumetric 250. And we've got 1.3 grams of HA in there, and this is used to fill up the burette. Okay, so that goes in the burette, and pipette is then added 25 centimeters cubed of sodium hydroxide of that concentration, so that goes into the conical flask below. So we've got 25 centimeters cubed of NaOH there. And the concentration of that is 0.112 moles per decimeter cubed. So we can find out, we know the volume and the concentration of the NaOH, so we can find out the moles of NaOH, which should then let us able to work out the moles of HA that we've got in the burette. Okay. Right, so let's do, and what we've got to do is calculate the MR of HA, 5-mark question here. Okay, so the titration results shown below, and we've got to, first of all, we've got to choose which ones are concordant and which ones we should use. So they've got to be within 0.1 of each other. So we can see that the only ones we have got with 0.1 of each other are these two, 26.4 and 20. So the average titer then is going to be 26.45 centimeters cubed. Right, so let's go ahead with this calculation. So as I said before, we can work out the moles of NaOH because we know the concentration and the volume there. Let's do that. So moles of NaOH in this titration, conc times volume. So that's going to be 0.112 moles per decimeter cubed, multiplied by 25 over 1,000, the volume in dm cubed. That gives us it's going to give us 2.8 times 10 to the minus 3 moles of NaOH. So that enables us to work out how many moles of HA we have got in the burette here. So look, we've got our HA in the burette. The titer was 26.45, and we know it is a 2:1 ratio. The equation there. So for every 2 moles of NaOH, we've only got 1 of HA. So the next thing I'm going to write down then is, so the moles of HA in the titer, which is 26.45 centimeters cubed, is going to be the moles equal to the moles of NaOH divided by 2, and that's going to be equal to 1.4 times 10 to the minus 3 moles. That's in 26.4. So now we can work out the concentration of the HA solution that we've made in moles per decimeter cubed. So let's do that. So concentration of HA is equal to the moles divided by the volume. The moles, we say we've got 1.4 times 10 to the minus 3, and the volume, well, that is 26.45 centimeters cubed, so 26.45 over 1,000. That gives us a concentration of 0.0529 moles per decimeter cubed. Right. Now we've got the concentration of HA. What we're going to do is we can work out how many moles of HA that we had in 250 and we know the mass, that's 1.3 grams of HA, so we know the moles and the mass, we can then work out the MR of HA. So let's do that. So, right, moles of HA into 50 centimeters cubed, that's 0.25 dm cubed, is equal to conc times volume. The concentration we worked out just now, 0.0529 multiplied by the volume, 0.25 dm cubed, that is equal to 0.01323 moles. Okay, so now we do the final step where you can work out the MR, because we know in 250 centimeters cubed, we've got 1.3 grams and we've got 0.01323 moles of HA. Right, moles is equal to mass over MR. Okay, so rearrange that, we get MR, which is what we've got to find out, is the mass divided by the moles. The mass is 1.3 grams. The moles is 0.01323. That is equal to 98.24. Okay, that is the MR, 98.24. Should really give it to 3 significant figures because all the data is given to 3 significant figures. So the MR is 98.2. That's our answer. Okay. Right. Now the uncertainty in using pipette in this experiment is plus or minus 0.06 centimeters cubed. Calculate the percentage uncertainty. So the percentage uncertainty is just the uncertainty, which is 0.06, over the actual measurement we made with pipette, which was 25 centimeters cubed, times by 100. Get that, and you will get an error of 0.24%. So the pipette counts for very little of the only a very small amount of error there. Okay. Right, 6.3. Right, before adding the solution from the burette in the rough titration, there was an air bubble. At the end of the titration, the air bubble was not there. Okay, so let's just draw that. If you got your burette, and let's say we've got an air bubble there. Here's the tap. Right, so if you, when you let that liquid come through, the volume is not all liquid, some of it is air. Okay, so some of the titer is air, some of the volume is air. Obviously that's not going to react with the alkali, so you're going to have to add a little bit more acid than, well, you think you're adding more acid, of course you're not, but you're adding more volume of stuff. It's because you measure out some air. Okay, during the titration, the student washed the inside of the conical flask with some distilled water. Okay, so you do that. You just wash around here, and that's in case you get any bits of acid splashing that don't go into the solution. So you wash them off so they go in. Why doesn't that affect the final titer? It's because the water, the distilled water here, does not react with the NaOH. You can say that. Or you can also explain it by saying, like, the total moles of NaOH hasn't been affected by adding water. Okay, the concentration of the NaOH doesn't matter. It's the number of moles you've got in the flask there. Okay, question 7. Right. So the reaction of magnesium and its compounds. Okay, group 2. Magnesium is used in the stages, one of the stages of the extraction of titanium. Given equation for the reaction between titanium 4 chloride and magnesium. Okay, so we've got titanium 4 chloride is TiCl4, and we're going to react that with magnesium. And the magnesium, you get a displacement reaction, you get magnesium chloride and you get left with titanium metal. Okay, so to balance that, we're going to need 2 magnesiums, and you get that. Okay, now what's the magnesium doing? What's it reacting as in there? It's actually a reducing agent. Why is it a reducing agent? Well, if you look at the magnesium, it's got an oxidation number of 0 in magnesium. In magnesium chloride, it becomes the Mg2 plus ions. It's got a +2 oxidation, so the Mg is oxidized. And of course, the thing that's becoming oxidized is the reducing agent. It reduces the titanium to the 0. If you like, titanium's got a -4 oxidation state there, sorry, +4 oxidation state, and it goes to a 0 oxidation state there. All right, calculation now. Magnesium oxide and magnesium hydroxide mixture, it's got a mass of 3,200, so that's 3.2 grams. It's reacted with carbon dioxide to form magnesium carbonate and water. And the amount of water you make is 210 milligrams, which is 0.21 grams of H2O. Calculate the percentage mass of magnesium oxide. So what we're going to do is, let's find out the moles of water first of all. So the moles of H2O made is equal to mass over mR. The mass of water is 0.21 over 18 is the mR of water. That gives us a number of moles of 0.01167. Okay. Now, if we look at the equation, we can see that 1 mole of magnesium oxide gives us 1 mole of water. So the moles of H2O, sorry, the moles of magnesium hydroxide, sorry, in the mixture has got to be equal to 0.01167. So let's find out what mass of magnesium oxide that is. Now, the mR of magnesium hydroxide is 24.3 for the magnesium, 2 oxygens, 16 each, and 2 hydrogens, so that gives us 58.3. Okay, so the mass of magnesium hydroxide is moles times mR, 0.01167 multiplied by 58.3. That gives us 0.68 grams. Okay. So they've got that much magnesium hydroxide, and the total mass was 3.2. So we just subtract to get the moles of get the mass of magnesium oxide. Then mass of MgO is going to be equal to 3.2 minus 0.68. That gives us 2.52 grams. Now we just got to work out the percentage of magnesium oxide. So the percentage is going to be the mass of MgO over the total mass times 100. That's equal to 2.52 over the total mass 3.2 times 100 gives us 70. To 3 significant figures, I get 78.8% there. Okay. Right, now distinguishing the following pairs of compounds in aqueous solution can be distinguished by the simple test tube reaction. So we've got to remember the solubility, the trends in solubility. So as we go down the group, magnesium, calcium, strontium, barium, the sulfates become less soluble. Barium sulfate is very insoluble. And the trend is the other way around with the hydroxides. They become more soluble. So the hydroxides, more soluble. Magnesium hydroxide is very insoluble. Barium sulfate is reasonably soluble. Right. So, how can we distinguish between sodium chloride and barium chloride? Well, we can show the presence of barium ions by adding anything containing sulfate ions, okay? But that's not a reagent. So you didn't get any marks for saying that. So anything with sulfate ions, the easiest thing you probably have to hand would be sulfuric acid. Dilute sulfuric acid, so that's going to be the reagent. What would happen with NaCl? No change. What would happen with barium chloride? You get a white precipitate. And the precipitate, of course, would be barium sulfate, but you don't need to say that. That's what it would be, though. Right, the next two comparisons, sodium chloride and sodium carbonate. Right, so this isn't really about group 2. Carbonates, if you add acid to them, if you add acid to a carbonate, well, for sodium carbonate, just write the equation. You don't need to write it. You are going to get sodium chloride, and you'll get carbon dioxide. So you'll get fizzing. You'll get effervescence always. Whenever you add acid to a carbonate, you get effervescence. You add acid to sodium chloride, nothing will happen. So the acid you're going to add here, probably add hydrochloric acid, sulfuric acid or nitric acid would be fine. Sodium chloride, no change. Observation of that, effervescence, which is fizzing. Okay. Right, onto the multiple choice questions then. Which sample measured at room temperature and pressure contains the greatest number of the stated particles? Okay, so if you want to find out the number of particles, you've really got to find out the number of moles, haven't you? Okay, and multiplied by the Avogadro constant. Let's call the Avogadro constant L. So how many moles of hydrogen molecules have you got? Well, H2 has got an MR of 2. So the moles in that one, you've got half a mole. So the number of particles is going to be half times by the Avogadro constant. 1 gram of helium atoms. Well, in this one, well, helium has a relative atomic mass of 4. So you're going to have a quarter of a mole. So a quarter times L, Avogadro constant helium atom. So that's less. Now these are so volumes of a gas. So the moles of a gas is standard temperature and pressure is equal to the volume in dm cubed over 24. So how many moles of hydrogen? That we've only got 1/24, which is way less than the other ones. So the number of hydrogen molecules is going to be 1/24 times L. And for helium, well, we've only got 1/24 moles of helium as well. So that's a lot less than the others. So the one we've got the most particles is going to be that one there, A, the hydrogen. Okay, so this is about working out empirical formula for molybdenum. Okay, now molybdenum is probably not one of those that you probably know the relative atomic mass of by heart, and the MR of molybdenum is 96. The atomic, I should say the AR of molybdenum is 96. Okay, so I'm going to say what are the moles of molybdenum? So let's write that. Moles of molybdenum, moles is equal to mass over AR. Okay, we want to work out the ratio of moles here. So moles MO is the mass, which is the molybdenum is 4 grams. So it's going to be 4 divided by the MR, which is 96. And then we've got our moles of oxygen here. Well, if 5 grams is 4 grams of molybdenum, 1 gram has got to be oxygen. Yeah. So we've got 1 divided by the AR of oxygen, which is 16. So if we just put the numbers in there, we get that's 0.416 moles. And that's 0.0625 moles. So that's the ratio of the moles. And what do we do to simplify the ratio? Divide by the smallest number. The smallest number we've got there is 0.416. So let's do that. We get 0.4106 divided by itself. And that divided by 0.0416. All right, that's obviously going to give us 1. This gives us almost exactly 1.5. So how can we get that number to whole ratio? We've got to double it. So that's an equal to a 2 to 3 ratio. So that means our formula is MO2O3. So our answer is C. Okay, this is a quick one to answer now. Which substance has delocalized electrons? Well, it's graphite, of course. Iodine is I2 molecules, no delocalized electrons. Sodium chloride is ions. Tetrachloromethane is small covalent molecules. So A is definitely the right one. Okay, next one about shapes of molecules. Which species is not pyramidal? Now, to have a pyramidal shape, is, if you remember, it's like nitrogen. It's like the ammonia, sorry. Ammonia, you've got 3 bonding pairs, and what makes it pyramidal is you've got this lone pair there, which, okay. So we want something with 4 bonding pairs and lone pairs, right? This one is pyramidal. Phosphorus is in group 5, just like nitrogen. So you will get 5 electrons on the outer shell. So PF3, if I just draw the dot cross diagram, I won't draw all the electrons in the fluorine. You're going to have a dot and a cross, a dot and a cross. And of course, we've only drawn 3 of phosphorus's 5 electrons, so it will have a lone pair. So that one is pyramidal. H3O plus. Well, if we've got a water molecule there, just like that, we have 2 lone pairs on the oxygen. Forms a dative bond to an H plus there to form the H3O plus ion. So we can see, yeah, we've got 3 bond pairs and 1 lone pair there, so that's pyramidal as well. These are both pyramidal. CH3 minus, not something we will come across. Let's just see what that is. So I'll just rub this one out. Right, so let's see, carbon is in group 4. So I'm going to draw okay, we've got 3 hydrogens, so we want a dot and a cross for each of those. Now I have drawn 3 of carbon's 4 electrons, so I need to draw 1 more, but it's CH3 minus here, so it's got an extra electron from somewhere else, so it does have a lone pair. That's got 3 bonding pairs and 1 lone pair, so that means BF3 must be the one that's not pyramidal. Let's just do that. Boron, of course, is in group 3 of the periodic table. Okay, so we draw a dot cross diagram for that. 3 fluorines there. So we want a dot and a cross, a dot and a cross, a dot and a cross. So that's 3 of borons, 3 electrons drawn, no electrons, no lone pairs. That's going to be trigonal planar, not pyramidal. So the correct answer is that one. Okay, what change occurs when water is vaporized? An exothermic change occurs. That's wrong, because you've got to break hydrogen bonds between the water molecules, and that's going to require energy. It's going to be endothermic. Covalent bonds are broken. No, you don't break any of the hydrogen-oxygen covalent bonds. Intermolecular forces are overcome. That's true. It's the hydrogen bonds are overcome. And the total energy of the molecule decreases. It doesn't. It probably increases because you have to add heat. You have to provide heat in order to do it. Okay. Right. Which equation represents the equation that has a standard enthalpy change equal to the standard enthalpy of formation? So we want elements in their standard states. That's what we want. Okay, the standard state of barium, it's a metal, it's going to be a solid, and chlorine, of course, is Cl2, gas. So that one is the right answer. A is wrong because the state symbol of barium is wrong. B is wrong because it's ions, and D is wrong because it's ions. It shouldn't be ions. 15. Which equation does not represent a redox reaction? Okay, well, This one does. If you look at hydrogen, look, hydrogen's got an oxidation number of 0 because it's an element there. And in all of its compounds, it's always +1. So the hydrogen has actually been reduced there. Magnesium has been oxidized, so that's not 1. Here, well, we can see this is definitely oxidation because you're adding oxygen onto methane. You can look at oxidation numbers if you want to do. Oxidation number of carbon there is -4, and in carbon dioxide it's +4, so that's been oxidized. Okay. So it's not that. Iron. Now you can see this is redox because iron is going to have an oxidation number of 0 here because it's an element, and in iron sulfate it's not an element anymore. The sulfate ion is 2-, so the iron must be a 2+ ion. It's got oxidation number of 2. The iron has been oxidized, and the copper, well, the copper has been reduced, we'll see, because the copper was a copper ion here, +2, and now it's an element, 0, so that's redox. You can see this one, there's no redox here. It's actually an acid-base reaction. Copper oxide is the base and hydrochloric acid is the acid. We'll just check it. Oxidation number of oxygen. Well, in all of its compounds, it's always -2. And it's in a compound there and in a compound there, so it's -2. Hydrogen is always +1 in its compounds. It's +1 there, and it's in the compound, it's +1 there. That hasn't changed. Copper, well, we can see in copper oxide, oxygen is always -2, so copper must be +2 there. And in copper chloride, well, the chlorines are both chloride ions, so that means you've got a Cu2+ ion there, that's +2 there. That's not a redox reaction. Okay, which property would you expect the element radium to possess? So if you're not immediately know where radium is, you can see, look, it's down there. It's the last one of group 2, the biggest group 2. Right, and now as you go down group 2, the sulfates become increasingly insoluble. Right, now so we can see there that radium would not be expected to form a soluble sulfate. It should be very insoluble, so that's wrong. Do the group 2 metals react with water? They all react with cold water except for magnesium and beryllium, they don't. So yeah, as you go down the group, they get more reactive, react with water. So that's wrong. It will react with water. Is it a good conductor of electricity? Yes, it will be because it's a metal. It's got delocalized electrons, and it won't form a covalent fluoride. It's a metal. It's going to form radium 2+ ions. It's going to form an ionic chloride, definitely. Magnesium, calcium, strontium, barium all form ionic chlorides. Beryllium's a bit funny; it doesn't, but you definitely expect barium to form an ionic fluoride, sorry, not chloride. C is the right answer. But statement is not correct, okay? Now, ionization energies, well, when we go down any group, you've got to remember when you go down any group, including group 2, the first ionization energy, decreases. The first ionization energy decreases. Right, so strontium will have a lower ionization energy than strontium because it's further down. That is correct. Strontium will have a larger ionic radius, and calcium is further down the group. It's got more shells of electrons. Strontium will react less vigorously. No, it won't. It will react more vigorously, so that's wrong because as you go down the group, they get more reactive, just like the alkali metals do. And strontium hydroxide is more soluble than calcium hydroxide. Yet as you go down the group, you get an opposite trend with the hydroxide solubilities. The hydroxides become more soluble. So that one is also correct. So C is the answer there. Okay, which is the best oxidizing agent? Well, oxidizing agents, what do? They remove electrons from things, yeah? Right. Fluorine is a very good oxidizing agent. It's it's because it's much better than any of the other halogens because why is it the strongest oxidizing agent? They all have some tendency to gain electrons to form the halide ions. Fluorine is the best though because it's the smallest atom, so the electrons that it gains are closer to the nucleus. So that is that's definitely better than iodine. So this looks like the promising one. Is the F- ion an oxidizing agent? It's not at all. It's got no tendency to gain electrons. It's quite happy. It's got 8 electrons in its outer shell, so it doesn't want to gain any more. The same with iodide. Is not an oxidizing agent. It doesn't want to gain any more electrons. It's got a full outer shell. So our answer there is fluorine. In actual fact, iodide is a reasonable reducing agent because it has some tendency to lose electrons. Okay. Right, this is an easy question, but it's put in a rather strange way. So we all know the equation for when we do these calorimetry experiments. Quantity of heat released is mc delta T. Okay, so it tells us the mass of water is m, well, we're using that there. The specific heat capacity of water is C. And the temperature rise, well, instead of called it delta T, they've called it Y. So what's the amount of heat energy absorbed, Q? Well, it's mcy. So it's that one. Okay. Yeah, don't be fooled by this by adding 273 just because the units are in Kelvin there. Because although 1 degree C is definitely not equal to 1 Kelvin, a rise of 1 degree C is equal to a rise of 1 Kelvin. Okay. So A is the right answer there. 21. Okay, this is about volume of any gas. 1 mole of any gas contains the same, has the same volume. Okay, so that means, so if you have 24 dm cubed of oxygen, it will have the same number of moles as 24 dm cubed of butane. And that means if you have 10 centimeters cubed of oxygen, it will contain the same number of moles as 10 centimeters cubed of butane, or 20 of will be the same as 20, and so on. So that's how we do these. So 20 centimeters cubed of butane, right? If you get 20 centimeters cubed of butane, well, that means 1 mole of butane gives you 4 moles of carbon dioxide. So that should give you 80 centimeters cubed of carbon dioxide. So that first one is wrong. Okay. So that's not correct. That will give you 80. Right. Now let's see this bit in here. It says if you get 0.65 dm cubed of oxygen, so that's 65 centimeters cubed. Now let's see. Well, that's wrong because look, 20 centimeters cubed of butane would actually need 6.5 times 20 of oxygen, and that's equal to 130 centimeters cubed. So that's wrong. 70 centimeters cubed of oxygen remain. Well, that is right because look, we've got 0.2 dm cubed, which is equal to 200 centimeters cubed. How much is used up? Well, we've worked out it's 130, so how much is left over at the end is 200 minus 130, which is equal to 70. So that one's right. Let's just check the last one. Steam. So 0.5 dm cubed of steam, that is like 500 centimeters cubed of steam. Well, you're not going to get that much because 1 mole of butane will give you 5 moles of steam. So 20 centimeters cubed gives you 5 times 20, it gives you 100 centimeters cubed, not 500. So that's wrong. So C is the right answer. Which statement is correct about reactions involving halide ions? Okay. Sodium chloride forms chlorine when added to concentrated sulfuric acid. It doesn't. Okay. Chloride ions, unlike bromide ions and iodide ions, cannot give their electrons away to sulfuric acid. Okay, so they can't. In other words, they can't be oxidized by sulfuric acid. So that does not happen. Okay, chlorine holds onto the electrons too strongly. Sodium chloride forms chlorine when added to bromine. Okay, so if you added Br2 to NaCl, would any reaction occur? It wouldn't, because, as I said, the chloride ions will not give their electrons to bromine because they're holding onto them more strongly. or if you like, in GCSE talk, chlorine is more reactive than bromine, so you're not going to get a displacement reaction. That's wrong. Sodium bromide forms bromine when concentrated sulfuric acid. That is correct. If bromide ions can be oxidized by sulfuric acid, the bromine doesn't hold on to the electrons quite strongly enough. You will get Br2, unlike chlorine. So that one is right. Let's just check the last one. Sodium bromide forms when bromine is added to iodine. Okay, so sodium bromide, hang on a minute. So NaBr, if you add that to iodine, no, you're not going to get a reaction there, because bromide holds onto its electrons more strongly than iodine can grab them, or if you like, iodine is less reactive than bromine, and so there's been no reaction there. So C is the right answer. Right, the last one now. Okay, percentage yield. 20 grams of aluminium are produced from 50 grams of aluminium oxide. Okay, so the MR of aluminium oxide is 102. So let's work out how many moles of aluminium oxide we've got. Is equal to mass over MR. So that is 50 grams of aluminium oxide. 50 over 102 is equal to is equal to 0.49 moles. Right, look at the equation. 2 moles of Al, this gives us 4 moles of aluminium. Sorry, 4 moles. So that means 1 mole of aluminium oxide is going to give us 2 moles of aluminium. So we're going to say, therefore, moles of aluminium, if we get 100% yield, should be 2 times 0.49, which is equal to 0.98 moles. Now let's work out the mass of aluminium if you get 100% yield. Mass aluminium is equal to moles multiplied by the AR. So that's 0.98. The AR of aluminium, relative atomic mass, is 27. That gives us 26.4 grams if you get 100% yield. So our percentage yield then is what we do get, which is 20 grams over what we would expect, 26.4, multiplied by 100. That gives us about 76%. So our answer is A. And that is the last question on the paper.